In the harsh arithmetic of modern warfare, the tyranny of distance is the ultimate enemy. A military force can possess the most advanced weaponry on the planet. But if it cannot sustain its frontline troops with ammunition, medical support, and reinforcements, defeat is mathematically inevitable. For over half a century, strategic planners have been handcuffed by a persistent operational gap. Fixed-wing strategic airlifters like the C-17 or C-130 offer immense range and payload capacity, but they are entirely dependent on intact, secure runways. On the other end of the spectrum, heavy-lift rotary wing assets like the CH-53K King Stallion provide vertical flexibility, but they are fundamentally limited by slow transit speeds and high vulnerability in contested airspace. The modern battlefield, characterized by anti-axis area denial or A2AD environments, demands a paradigm shift. Enter the MV-75 Cheyenne II. It is not merely an aircraft, it is a strategic bridge, engineered to combine the speed and altitude of a turboprop with the vertical dexterity of a helicopter. The Cheyenne II is rewriting the doctrine of contested logistics. To understand the Cheyenne II, we must look at the lessons learned from the first generation of tilt-rotor technology. Early platforms proved the concept was viable, but they were plagued by high maintenance hours, mechanical complexities, and catastrophic vulnerabilities during the critical transition phase between vertical and horizontal flight. The MV-75 was born from a rigorous zero-based design philosophy. The Department of Defense requested a platform capable of lifting twice the payload of legacy tilt-rotors while drastically reducing the acoustic and thermal signatures. The resulting airframe is a masterpiece of aerospace engineering. The fuselage is constructed from next-generation aero-elastic carbon composites materials, originally developed for low-Earth orbit spaceplanes. This aerospace-grade skin is 40% lighter than traditional aircraft aluminum, but offers a structural integrity capable of withstanding extreme aerodynamic stress. More importantly, the composite materials feature embedded radar-absorbent properties, significantly reducing the aircraft's cross-section on enemy early warning systems. The beating heart of the Cheyenne II is its revolutionary propulsion system. While legacy tilt-rotors relied on a precarious dual-engine setup mounted directly on the wingtips, the MV-75 utilizes a distributed power generation system. For advanced turboshaft engines are housed deep within the reinforced wing roots, rather than on the rotating nacelles. These power plants generate a combined output exceeding 25,000 shaft horsepower. Power is transferred to the massive variable geometry proprotors via an intricate redundant network of interconnecting drive shafts. This architecture is a quantum leap in aircraft survivability. Should the MV-75 take catastrophic enemy fire and lose one or even two engines on the same side, the flight computer instantly redistributes the remaining power across the drivetrain. The aircraft can maintain a stable hover and execute a safe vertical landing, turning what used to be a fatal scenario into a manageable emergency. Once in horizontal flight mode, the Cheyenne II commands a sustained cruise speed of 350 knots, with a service ceiling pushing 25,000 feet. It operates above most low-level weather systems and out of range of standard man-portable air defense systems or In the era of multi-domain operations, hardware is only as effective as its software. The Cheyenne II was not designed as a standalone transport. It is a flying data node, integrated directly with low-Earth orbit satellite constellations. The MV-75 possesses continuous encrypted bandwidths ensuring uninterrupted communication even in heavily jammed electronic warfare environments. But its most lethal capability lies in its capacity to act as an airborne mothership. The Cheyenne II's internal cargo bay is modular. It can carry a standard payload of armored vehicles or infantry, but it can also be configured to deploy air-launched effects, specifically autonomous drone swarms. While cruising at high altitudes, the MV-75 can release hundreds of loitering munitions or sensor drones. Using advanced swarm intelligence algorithms, these drones fan out to map enemy air defenses, conduct electronic warfare, or execute kinetic strikes. The loadmasters in the back of the Cheyenne II, utilizing AI-assisted command consoles, monitor the swarm in real time, effectively clearing a safe corridor for the aircraft before it ever reaches the landing zone. Deploying to a hostile drop zone requires more than just speed. It requires armor and evasion. The MV-75 features a sophisticated active protection system. Its directional, infrared countermeasures or DIRC utilize advanced lasers to blind incoming heat-seeking missiles. When descending into a hot landing zone, the Cheyenne II utilizes a computerized brownout protocol. In desert or snowy environments, rotor downwash creates blinding clouds of debris, disorienting human pilots. The MV-75's onboard millimeter-wave radar and LiDAR map the ground beneath the aircraft in real time, feeding a synthetic, high-definition 3D terrain model directly into the pilot's augmented reality helmet. The aircraft effectively lands itself with millimeter precision, even in zero visibility conditions. Tactically, this allows for distributed lethality. Commanders can now bypass heavily fortified beaches or air bases, inserting heavily armed expeditionary forces directly into the enemy's rear echelon. The MV-75 strikes with the speed of a jet, delivers the punch of an armored column, and vanishes before a counterattack can be organized. The introduction of the MV-75 Cheyenne II forces a global reassessment of military logistics. However, this superiority comes at a steep financial cost. With a staggering procurement price and demanding maintenance hours, it requires a robust defense budget to sustain. Yet, military strategists argue that the return on investment is unparalleled. In a future conflict spread across the vast expanses of the Pacific or the rugged terrains of Central Asia, the side that controls the logistics controls the outcome of the war. The Cheyenne II is more than a triumph of engineering. It is the realization of a decades-old dream to conquer the tyranny of distance. It ensures that no matter how remote the battlefield, the supply line remains unbroken. Thank you for joining us for this comprehensive technical analysis here on Hive Command. If you value deep dive, defense journalism, and aerospace analysis, make sure to subscribe and hit the notification bell.